the last elastic constant we're going to consider is shear modulus. So shear modulus considers the material response on the shear. Okay, so suppose that you have originally square shape material, and under the shear stress like a tau xy and tau yx, you can expect the change of the shape. Okay, so originally like the angle was pi over 2 here, pi over 2 here, and due to this shearing stress, you're gonna expect change in the angle pi over 2 plus gamma or pi over 2 minus gamma. Okay, so shear modulus G connects the relationship between shear stress tau and the shear strain gamma. Okay, so for xy shear stress, you're gonna have gamma xy. For yz and for gx shear stress, you're gonna have gamma yz and gamma gx. Okay, and shear modulus connects shear stress and shear strain. Okay, so that's the definition of shear modulus. And can we have the relationship between shear modulus and Young's modulus and Poisson ratio and bulk modulus? And answer is yes. So before talking about the connections, let me show you one example of utilizing the shear modulus to obtain the displacement of simple shear material. So here we're going to consider originally square shape material. Original shape was this square. Now under this force P here, and original length in y direction is Ly. You expect displacement in x direction for top plate, right? The top plate would move here and the bottom plate will stay there due to this rigid wall and perfect adhesion. And starting from originally pi over 2 after shear, you expect pi over 2 minus gamma here. This is angle gamma, and you can express gamma here, right? This is the angle gamma. So this angle gamma can be approximated as tangent gamma, and tangent gamma is defined as delta x over Ly, the length in y direction, and the shear stress. Suppose that we have cross-sectional area here. The area on top surface is A, then P over A is given as tau. Okay, and if you make a relationship between tau and gamma, this is tau and gamma, and the relation is connected through the shear modulus G. Okay, so if you use this relationship, you can obtain how much top plate displayed using the formula delta x equals to be force P times length along the y direction Ly, and shear modulus divided by shear modulus G and top area A. Okay, top surface area A. Okay, so this is how you obtain and how you utilize shear modulus to obtain the deformation of material under shear. Okay, so to summarize, so I can say following. So under the uniaxial loading, you can make a relationship between sigma x and epsilon x using Young's modulus, and the relationship between axial direction and lateral direction strain can be characterized by Poisson ratio nu. And on the hydrostatic loading, where sigma x, sigma y, and sigma z are equal to each other, you can define the volume fraction change using so-called bulk modulus, and typically our textbook use K, and K has a relationship between Young's modulus and Poisson ratio like E over 3 multiplied by 1 minus 2 nu. Then under shear loading, we can make a connection between shear stress and shear strain using G, which is shear modulus. Then of course the natural question is there any relationship between G and E and U and K? And of course the answer is yes. Okay, so to answer this, let's think about one example problem. So here we're gonna consider this square shape sample. Originally it has a square shape, and the length of each surface is 2. Okay, and each of this half surface has a length of 1. Okay, for our conveniency. Okay, now if this square material is under axial tension along x direction, then this is what you can expect. along the x direction, this original length of 1 will extend it to 1 plus epsilon x. And along this lateral direction, originally 1, but now it's 1 minus nu times epsilon x. And please think about the definition of epsilon. The definition of epsilon is delta L over L for each direction. Then you will understand this why. And if you don't get it like right away, it's natural. Once you get practice with a lot of homework problems and sample problems in ME231, you're gonna get used to it. Okay. Now this is the change of the shape for the original entire shape. Instead of considering the entire volume, let's think about this imaginary volume within this sphere. It originally have this pi over 2 angle for all of these the angles, okay, but after the tension you have change of the shape. Okay, now let's try to obtain the stress acting on this oblique plane, and that's what we have done. So for stress acting on this oblique plane, we found that tau must be written as sigma sine theta and cosine theta, and here the theta is 45 degree, so you have 1 over square root 2 and 1 over square root 2 for sine and cosine. So tau must be same as sigma over 2, and sigma is the applied normal stress for entire sample. Okay, so when you imagine this imaginary sphere inside the big sphere, and this imaginary sphere is under combined loading, normal stress and shear stress, and only shear stress changes the angle here. This is shear stress and this is shear strain must be connected. Okay, and to obtain the and the relationship between the stress and strain must be obtained through the shear modulus, and this is how we gonna connect the Young's modulus and Poisson ratio with the shear modulus ultimately, because this shear modulus will have connection with applied normal stress sigma. And let me keep massaging the equation. Okay, so now because we already obtained the tau as a function of external normal stress sigma and the angle theta, let's try to get relationship between normal strain sigma epsilon x and the shear strain gamma here. Okay, so let's focus on just one piece of the triangle here. Okay, so for this triangle, it has 1 minus nu epsilon x, and the length in this direction is 1 plus epsilon x. Okay, and this is how you write down its geometry: 1 plus epsilon x, 1 minus nu epsilon x. The angle is pi over 4, originally 45 degree angle, but now after shrinkage it becomes pi over 2 minus gamma over 2, because gamma is the change of angle for this entire range. Okay, now here out of this triangle we can define tangent pi over 4 minus gamma over 2 using the ratio between this length and that length, 1 minus nu epsilon x, and divided by 1 plus epsilon x. Now it's time to use trigonometry equation. So until now I cannot memorize the trigonometric relationship. Maybe you can Google it. So I always Google trigonometric relationship. So from Googling you can find that tangent alpha minus beta can be written as this way. So you can decompose pi and gamma from numerator and denominator. So you're gonna have this is alpha and this is beta for this equation. So you have tan pi over 4 and tan gamma over 2, and in the denominator you have 1 plus tan pi over 4 and tan tangent gamma over 2, and this guy is simply 1. You put 1 here and you put 1 here, it becomes simply 1. So you have 1 minus tangent gamma over 2, denominator you have 1 plus tangent gamma over 2. Okay, so this is how you how you can make simpler this relationship, tangent pi over 4 minus gamma 2, like this. Okay, now if you look at this and if you look at this, you can make a relationship between epsilon and gamma in easier way. Okay, so this is our exact equation when the deformation of material is really small, when gamma is really small, so that gamma can be approximated as like a tangent gamma. You can rewrite this as gamma over 2, you can rewrite this as gamma over 2. Then what you can do is you can massage the equation so that you after massaging the equation you put your gamma in left hand side and all the other term in the right hand side. Okay, and what you're gonna do is after looking at this expression, you're gonna do a simple Taylor expansion for first order. So when you have these kind of equation, you have you can approximate this as 1 minus x if you only consider x to the first power. If you consider x to the second power, you're gonna have another terms, according to the Taylor series. But because epsilon x itself is really small number, we'll only consider the first order approximation of 1 over 1 plus 1 minus nu over 2 multiplied by epsilon x. Okay, then you can rewrite gamma in terms of epsilon x after removing all second order term like epsilon x square term. Then you're gonna end up having gamma is equals to be 1 plus nu multiplied by epsilon x. Okay, so here like one complexity that some of you may feel is if you didn't study freshman calculus very well, you're gonna get confused in many different places. Okay, so because we are considering like a small material response and linear response, we're gonna use like a Taylor expansion up to first order in several places. If you get confused about these kind of approximation, please read the Taylor expansion chapter in freshman calculus book, and please try to get used to this approximation. Okay, so after making connection between gamma and epsilon s, and after making connection between sigma and tau, okay, then what you can do is using this equation and using that equation, okay, then using also that equation and that equation, after combining all of these equations, what you can realize is that you can finally find g equals to be e over 2 times 1 plus nu. Okay, so please do this practice by yourself. Okay, so what's the implication? This is same as like a bulk modulus. Okay, so g must be larger than 0 because you don't want to have a material such that when you apply force in right direction, the material tries to deform in opposite way. Okay, so to prevent this unphysical phenomena, material should have positive shear modulus. To have a positive shear modulus, Poisson ratio must be larger than -1. Okay, so from this physical condition, k must be positive and shear modulus must be positive. The Poisson ratio must be larger than or equal to -1, and smaller or equal to 1 over 2. Okay, so this is the range of Poisson ratio you can find in nature and real world. And you're gonna get confused about, is it possible to have negative Poisson ratio material? And yes, there is negative Poisson ratio materials, and you can tune the Poisson ratio by tuning the structure. Actually, when you look at the pattern of the Nike shoes, like at the bottom, you're gonna see like a negative Poisson ratio patterns, and it is called auxetics. Or this is material with negative Poisson ratio. And if you get curious about this material, please Google auxetics, and if you Google auxetics Nike shoes or auxetics for shock absorbing, there will be tons of documents in Google search. Okay, so if somebody asks you what will be the range of Poisson ratio, perhaps in the interview for KAIST graduate school, then you can say that the Poisson ratio should be larger than or equal to -1, and smaller and equal to 1 over 2. And if somebody asks like is there negative Poisson ratio, is it possible, and you can say yes, of course it's possible, and it's used in several engineering applications already. Okay, so anyway, we made a connection between shear modulus and Young's modulus and Poisson ratio now in this video. So what we made the connection between K, G, and nu and E, and there is two equations connecting these four constants. So out of four constants, we have two equations. So in other words, out of four elastic constants, we're gonna have only two independent material properties. Okay, so please remember that out of these four, we have only two independent property, or if you know only two out of four, you can obtain the other two for free using the relationship between G E nu or K E nu. Okay, so with that, let me close the video on elastic constants here.